Model for finding frequent sets in FP growth for multimodal data. There is no doubt that in the last few years, machine learning, artificial intelligence has been gaining in popularity. Because big data is currently the hottest trend in the technology industry, ML is incredibly effective for forecasting and calculating proposals based on large amounts of data. This work is based on one of these algorithms, it's the FP growth algorithm. FP growth, or frequent pattern growth, is a reasonably young algorithm. FP growth offers a radical approach to abandon the generation of candidates. Generation of candidates is the basis of the a priori algorithm. Theoretically, this approach will further increase the algorithm's speed and use even less memory. This is achieved by storing the prefix tree in memory, not from combinations of candidates, but the transactions themselves. FP growth is an improvement on the a priori method. Disadvantages of the a priori algorithm are: to use a priori, you need to generate sets of candidates. These elements can be significant if the set of elements in the database is also significant. A priori requires multiple database scans to verify support for each generated set of items, resulting in high costs. These shortcomings can be overcome using the FP growth algorithm. This algorithm is an improved method of a priori. Frequent regularity is formed without the need to generate candidates. The FP growth algorithm represents a database in a regular pattern tree or FPG tree. This tree structure will keep the link between the set of elements. A single frequent element fragments the database. This fragmented part is called a pattern fragment. Sets of elements of these fragmentary patterns are analyzed. Thus, the search for frequent sets of items is relatively reduced with this method. FP growth algorithm steps. The first step is to scan the database to find the origin of sets of elements in the database. The first step is the same as the first a priori step. The number of sets of the first element in the database is called the number of support, or the frequency of the set of the first element. The second step is to build an FPG tree. To do this, create the root of the tree. The root is represented as a zero value. The next step is to rescan the database and check the transactions. Examine the first transaction and find out the set of elements in it. The set of elements with the maximum number starts at the top. The next set of elements with a smaller number is below. This means that a tree branch comprises a set of transaction elements in a descending order. The next transaction in the database is studied. Sets of items are arranged in descending order. Any set of elements of this transaction is already present in another branch, for example, in the first transaction, then this branch has a common prefix to the root. It means that a shared set of elements is associated with a new node of another set of elements in this transaction. In addition, the number of items increases as it occurs in transactions. The total node and the number of new nodes increases by 1 as they are created and linked according to transactions. The next step is to develop the created FPG tree. To do this, the lowest node is examined first together with the links of the lowest nodes. The lowest node represents the frequency of the pattern of the size 1. From it is the path along the tree FPG. This path is called the conditional template base. Conditional template database is a database that consists of configuration loop in the FPG tree that means the lowest node suffix. Conditional tree FPG is constructed, which is formed by counting sets of elements on the path. The FPG tree considers the sets of elements corresponding to the threshold support. Frequent templates are generated from the FPG tree. Advantages and disadvantages of the FP growth algorithm. Advantages are: the algorithm should scan the database only twice compared to a priori, which scans transactions for each iteration. Pairing elements is not done in this algorithm, making it faster. The database is stored in a compact version in memory. It is efficient and scalable for extracting long and short frequent circuits. Disadvantages are: FP-wood is more cumbersome and challenging to build than a priori. It is more expensive. As the database is extensive, the algorithm may not fit in the shared memory. FP growth is an improvement on the a priori method. Result of the frequent pattern tree. An appendix to the FP tree requires a header table to indicate the first instance of this type. The header table will allow you to quickly access all the elements in the FP tree. In addition to storing pointers, you can use a header table to keep track of the total number of items of each type in the FP tree. The updateTree function increases the FP tree with a set of elements. Figure 1. A. Scan the database to find sets of items in the database. B. the root is represented as a zero value. C. A tree branch is built from sets of transaction elements in descending order. D. The branch of the transaction has a common prefix to the root. And E. Increased by one total node and the number of new nodes. Here's the generated frequent sets. Development algorithm for solving a functional problem. There are three main steps to finding frequent sets of elements in the FP tree. Step 1. Get a database of conditional templates from the FP tree. Step 2. From the base of conditional templates, we create a conditional FP tree. And step 3. Recursively repeat steps 1 and 2 until the tree has only one element. Comparison of a priori and FP growth algorithms by number of transactions, x, and time, y. Based on the research, it can be argued that the FP growth algorithm is much more efficient and faster than a priori algorithm. Comparative studies of the classical a priori algorithm and FP growth have shown that the number of transactions in the data network increases, the time spent searching for frequent subject sets grows much slower for the FP growth algorithm than for a priori. Conclusions. FP growth algorithm is an efficient way to find frequent patterns in a dataset. FP growth algorithm works on the a priori principle but much faster. The a priori algorithm generates sets of candidates elements and then scales the dataset to see if they occur frequently. The FP growth algorithm is faster because it passes the dataset only twice. The dataset is stored in a structure called an FP tree. After building an FP tree, you can find frequent location of elements by finding conditional bases of the component and creating a conditional FP tree. So this process is repeated, specifying more details until the dependent FP tree has only one element. The FP growth algorithm can search for frequent words in a series of text documents. Applying the FP growth algorithm on a specific topic can give you brief information about the topic.